Hello everyone. Today the topic of my presentation is RFIC module design, MMIC amplifiers. The amplifier is an essential component of the wireless communication system. In this chapter, the basic theory of the MMIC amplifier is presented, including descriptions of DC bias injection, classical stability and gain analysis, different types of noise, such as thermal noise, short noise, flicker, and propagation noise, are briefly reviewed. And lastly, the practical designs of the MMIC IF amplifier, the cascade low noise amplifier, and the three-stage power amplifier are illustrated. The most important aspects of the design considerations for microwave transistor amplifiers are the stability, the power gain, the bandwidth, the noise, and the DC requirements. This section deals mainly with the DC bias injection, the problems associated with stability and gain. The transistor must have DC bias to operate and can be set to an operating point to show the 1 to 5 characteristics, and the AC microwave signal swings above this value. Figure 3.1 shows schematically the 1 to 5 curves of a generic FET, indicating the four most common operating points used for an amplifier. Point 1 means low noise operating point. Point 2 is when the VGS is equal to 0 voltage, ID is equal to IDSS. Maximum small signal gain but high DC power consumption and noise. Point 3 is the middle of the I to 1 to 5 curve for maximum linear output power. Point 4 is higher efficiency with degraded linearity. The gate and drain DC bias voltages can be applied to a FET in a number of methods, as illustrated in Figure 3.2. In Method A, the drain voltage is required to be positive, and the gate voltage is required to be negative. It's convenient to find a topology with short inductors, through which the bias can be applied. In Method B, high-value resistors are used to apply the bias voltages, with the exception of low noise and high power amplifiers. This is a very suitable technique for establishing the gate bias because the gate draws no current and the resistor can be used to stabilize the device. In Method 3, short current circuit microstrip stubs are used. The short circuit end is grounded with a decoupling capacitor so that the DC bias can be applied. In Method D, the self biasing technique is used, enabling the FET to be biased from a single power supply rail. The advantages associated with the single power supply are significant, particularly for battery operation, but there is a general penalty caused by the slight increase in DC power consumption. One drawback of the technique is that it removes a useful post-fabrication tuning mechanism from the amplifier because the bias is fixed. There are many applications in which low DC current is more important than the ability of the device to operate at low drain voltages. Such applications can include battery-operated communications terminal in which the supply voltage is fixed but ultra-low DC power consumption is required. For this type of application, the staked bias technique is very attractive. This is best illustrated by studying the three-stage amplifier circuit diagram shown in figure 3.4. The stability of an amplifier is a very important consideration in the design and is decided based on the S-parameter of the active device as well as matching and termination. This chapter gives details of the theory and improvement in stability. Stability consists of two conditions, denoted as unconditional stability and conditional stability. The conditions for unconditional stability at a given frequency are given below. All coefficients are normalized to the same value. The stability circle expresses the stability of a circuit and is a term used in the network's S-parameter. The stability circle helps to achieve a stable amplifier graphically. Figure 3.5 shows the stability circle on a Smith chart at the output plane, and the shaded region in Figure 3.5 is the stable region. Figure 3.6 shows the circle of unconditional stability. There are some methods for improving the stability. First is resistive loading. Transistor stability can be improved by adding small series or large shunt resistors to the input or output, as shown in Figure 3.7. The designer should ensure the connection resistors in series or in a shunt. This is decided after the designer sees the stability circle of the circuit and the input and output stability circle are illustrated in Figure 3.5. Based on the stability cycle or the stability factor, it's determined whether a given circuit is stable or unstable. The second is the feedback method. Most amplifiers incorporated some form of feedback. It's interesting to note that the theory of negative feedback has been developed by electronics engineers. Feedback can be either negative or positive. The negative feedback is applied to this amplifier design. This is the noise consideration part. In this part, we will introduce some different noise. The first is the thermal noise. Johnson measured it. Nyquist explained it. Brownian motion of charge carriers in a conductor creates a randomly varying current, leading to random voltage. The characteristics of this is the amplitude follows a Gaussian distribution. It is described statistically. The second is short noise. The basis is the granular nature of electronic charge. The conditions for occurrence is presence of direct current flow, existence of a potential barrier for charge carriers to hop over. The characteristics of this is not present in ordinary linear resistors, arises from discrete electron charge hopping energy barriers. Current pulses are random, leading to white noise. Depends on electron charge, total DC current flow, and bandwidth. The third is the flicker noise. It's the most mysterious type of noise. It's usually found in various phenomena such as cell membrane potentials, Earth rotation rate, classic radiation noise, and transistor noise. The characteristics is fluctuations exhibit a 1 divided by f frequency dependence, often called pink noise. The fourth noise is popcorn noise. It is seen in semiconductors, especially point contact diodes, ordinary junction, and tunnel diodes. The characteristics is poorly understood similar sensitivity to contaminations as 1 divided by f noise. It is random intermittent noise pulse. This section addresses the practical MMIC amplifier design. 3 amplifier types are mentioned, including the IF amplifier, the low noise amplifier, and the power amplifier. The IF amplifier is designed as a two-stage amplifier, and the low noise amplifier is designed by cascade configuration. The power amplifier is designed with the three-stage configuration for CDMA applications, and each type of amplifier is fabricated and measured. The first is the IF amplifier design. A block diagram of the Q-band low-noise block down converter is shown in Figure 3.10. The LNB has the function of converting frequencies from satellites to the set-top box. The converter accepts an RF into 11.71 to 12.75 GHz and generates an RF output of 1032 to 2072 MHz. The local oscillator frequency is 10.678 GHz. The linearity, noise removal, and frequency conversion and application are the major performance parameters of the LNB down converter in satellite broadcasting. The amplifier schematics are shown in Figure 3.11. Each stage was designed for the flat gain to cover the entire broadband range well. Two stages are used in the common emitter configuration for the broadband IF amplifier. Lossy matching was employed for the resistors within the amplifier matching networks to achieve flat gain over the broadband. The most normal topology is the use of resistors in series with matching circuits as shown in Figure 3.12. Amplifier small signal gains and return losses are measured on chip by applying the CPW configuration to the text fixture using GSC buffer probes. The gain is 27 dB from 950 MHz to 2 GHz, lowered by 3 dB in comparison to that of the simulation results, and the flatness is 1.5 dB based on the difference between the maximum gain and the minimum gain, as shown in Figure 3.13. The input return losses are 24 dB and 20 dB. The output return losses are 12 dB and 9 dB. When the IF input power is minus 25 dB, the IF output power is 3 dB, as shown in the Figure 3.14. The simulation and measurement results are shown in Table 3.1. The layout was accomplished using a cadence tool as shown in Figure 3.15a, and Figure 3.15b shows a micro photograph of the fabricated in-gap HBT broadband MMIC IF amplifier. Next is the cascade RNA design. This section presents the feasibility of integrating the image reject filter into a cascade low noise amplifier for the Q-band low noise block down converter in a direct satellite broadcasting system as shown in Figure 3.16. The cascade RNA depicted in Figure 3.17 was designed by utilizing the 6-inch in-gap gas high linearity HBT technology of Keiku in Korea, and used the vertical bipolar intercompany module to extract accurate large signal characteristics of the in-gap gas HBT. The die size of the fabricated cascade RNA depicted in Figure 3.19 is 850 unimeter multiply 800 unimeter. The die was then attached to the gold-coated Teflon substrate by using silver, and wafer-level probe testing was performed. The cascade RNA produced a gain that was greater than 6 dB in the passband when the tubal image reject notch was turned off, and it can be observed that the 20 dB image rejection radio was exhibited below 9.25 GHz as depicted in Figure 3.20. The passband gain and noise figure response are displayed in Figure 3.21. The gain variation was kept small between 1.2 dB and 1.6 dB for switching the image reject notch on and off, respectively. The characteristic of the 1 dB gain compression point was measured by varying the 12.22 GHz RF input power of the cascade RNA between -13 and 0 dB as shown in Figure 3.24. This part is the power amplifier design. A power amplifier is a system component whose main task is to increase the power level of the signal at its input to a predefined level. In contrast with low-level amplifiers, often specified in terms of small signal gain, the absolute output power level is the main feature of the PA. Therefore, it's important to choose the proper device. The power amplifier is organized into a three-stage amplifier, depicted in Figure 3.23. This PA was designed by utilizing the 6-inch in-gap gas high linearity HBT technology of Keiku Inc. Korea, and used the vertical bipolar intercompany model to extract accurate large signal characteristics of the in-gap gas HBT. The PA ultimately can be considered from the energy perspective as a component converting DC power from the supply into microwave power, driven by an input power. This process is schematically depicted in Figure 3.24. The effectiveness of this conversion process is usually described in terms of the amplifier's efficiency or the conversion efficiency, which is defined as the ratio between the output RF and the supplied DC power. This efficiency is often called the drain efficiency or the collector efficiency and is given by in the next formula. In Figure 3.25, the power transfer characteristic of a Class A amplifier with two different output matching conditions is shown. The solid line shows the response of an amplifier that has been conjugate matched at significantly lower drive levels. The 2 points A and B refer to the maximum linear power and the 1 dB compression power respectively. The die is attached to the gold-coated Teflon by using silver epoxy, and then the wafer-level probe test is performed. The PA is focused on CDMA application. Figure 3.27 shows the max available gain and the S21 gain. The S21 gain is higher than 25 dB in the CDMA band. Figure 3.28 deficits stability in the band. In this bandwidth, the stable factor is over 1 and the power amplifier is a stable state. Figure 3.29 shows the P1 dB for 34.559 dB. OIP3 and IIP3 can be calculated by knowing the value of IMD, which is explained in Chapter 5. Figure 3.30 shows the PAE as a function of the input power. The fabricated three-stage PA is shown in Figure 3.31. The third stage or last stage of the PA consumes significantly more current than either of the previous two stages. Therefore, bonding wires are used in the output parts, and Figure 3.32 is the PCB board used for measurement. My presentation is over. Thank you, everyone.